So good afternoon, everybody, and I would like to welcome you to this first webinar on LISTalks on Energy Transition. So this is the first of a series, and it's on the topic of dominant role of power electronics in modern power systems. So this webinar will have two presenters, Pedro Rodriguez and Jan Svensson, who will give two perspectives of the energy transitions challenge and the role of power electronics. But first, a couple of words on the LISTalks conference series. So this is the first webinar of a series that aims at bringing together stakeholders, researchers, industry, and authorities. And the aim is to answer the state-of-the-art research and innovation questions that relate to our environment, climate change, sustainability, both in terms of strategies and design. This first webinar is preceding what will be the Energy Transition Dialogue 2022. This is an event that will be hosted by LIST in the 30th of June 2022. And in this session, we will provide an overview of the trends and new solutions that are developed by the industry in order to respond to the new challenges and opportunities arising in new power systems. It will then go on to discuss the paradox of how the most modern grid-connected converters have been inspired in the synchronous machines that were developed more than a century ago, and how they are still being used in relevant applications today. I would also like to inform you that the session will be recorded, and all attendees are free to put their questions in the question box that you have there in your screen during or after the presentations, but you can do it during the presentations as they go along. And all of these questions will be answered at the end of the session by the speakers. So that being said, we move to the first presentation on the industry perspective, and this will be done by Jan Svensson. So Jan received his PhD and his docent degree from Chalmers University of Technology in Gothenburg, Sweden. From 1999, he was with ABB in different R&D roles. In addition to his current role as research fellow within Hitachi Energy, he's also been an adjunct professor with the Chalmers University of Technology since 2018. His research interests include design and control of power electronics and power systems, power quality, storage technologies, and renewable energy. So with this, I pass the word to Jan for this first presentation. Thank you.
Thanks. Let's jump directly to the content. So I will say some words about Hitachi Energy, and then we move on to the power system evolution and energy transition. And here I will give two examples, one on mitigate low inertia and the other one on DC transmission. Next, we move on to the future view of the power electronics across the total power system. And finally, I will give a summary. So ABB sold its power grids division to Hitachi, and this division is now called Hitachi Energy. And we are around 40,000 employees around the world. Down left here, you could see the different customer segments. Mainly it is for utilities, but also for industry, transport, and infrastructure sector. And to the right here, you could see where in the world we are. So we are equally distributed, I would say, around the globe. And we have 4 global business units. We have grid automation, grid integration, high voltage products, and transformers. And in all these areas, we are the global technology and market leaders. And to be a market leader, we have a large global R&D organization that also includes 7 research centers. And I myself, I am located in the research center in Sweden, here in Västerås. Then you could also see here on the map that we have 3 other centers in Europe, 2 in North America, and 1 in Beijing, China. And we are employing new team members continuously. So if you are interested, just contact us. Okay, let's now go to the power system evolution and energy transition. So when looking into the future, it's always good to see where we come from. So therefore, I start in the beginning of a power system, what you could see at top left here. So we have had the battle of AC versus DC and AC1. So then we are building small electrical islands with different frequencies and voltages. We have short distances. It's a radial system. And in that time, everyone realized that bigger is better. So we start to build bigger grids into large grids, where we have large power stations, we have high voltage transmission lines, we go from radial to mesh grids, and we have passive loads. And of course, we have some issues with stability. We have a first swing stability issue, and of course, we want to avoid voltage collapses and inter-area oscillations. And one way to avoid this, a part of the solution has been to use synchronous condensers. So with synchronous condensers, we can increase the short circuit power and we can control the voltage level. However, a synchronous condenser has some disadvantages. So therefore, in the 70s, we start to replace the synchronous condensers with static VAR compensators using thyristors. Then if you continue here, later on, we started to have sensitive loads in the power system. And this is mainly computers and automation. So there the cost of low power quality increased a lot. And in the same time, we start to use power electronic loads. And early on, it was mainly thyristors and diode rectifiers. So in this case here, it's important to then mitigate and ride through voltage dips, and to mitigate voltage and current harmonics. And this we did with active power filters, and we continue to use reactive power compensation. But now we start to see a shift from the SVCs using thyristors to STATCOMs using transistors. And now we come up to today's power system, where we have a large amount of power electronic loads, and we have started to introduce distributed renewables using power electronic interfaces like for solar and wind. And the issue here now is that we start to get lower short circuit power, and we start to have a risk of interaction between the converters. So now it's important to have a robust controllers for the converters that could handle this. And also in the same time here, we start to see an increased use of HVDC transmission links. Now I would like to say some words about a few mega trends that are important. The first one is climate change. So we all know that we need to reduce the CO2 emission, and therefore we have now launched the energy transition globally. Another mega trend is urbanization. More than half of the world's population lives in cities today, and this will increase. A third mega trend is actually electrification. So the electricity consumption is growing twice the rate of the overall energy. And the next trend here is automatization and digitalization. So when we become more and more digital, the cost of non-performance of electrical system is increasing continuously. And talking about digital, we could say that number of data centers increases continuously. And finally, we have the fossil-free transportation, where we could start to use biofuels, but probably it will be even more on the electrical vehicles, where we use batteries and electrified highways. And for both these batteries and electrified highways, we will set tough demands on the infrastructure. Here I have a slide on a scenario on the energy transition up to 2050, and I'm taking these two figures from DNV's Energy Transition Outlook 2021. So to the left here, you can see the global electricity demand by different sectors. The important thing here is to see that the use of electricity will go up a lot from today around 2020 up to 2050. And to the right, you could see where does this electricity generation come from. And it will mainly be a lot of renewables that will cover this increase. but also cover the decrease of coal power and oil power. We are also see a change in the grid structure, where we go from the old structure of unidirectional power flow, passive loads, and we have loads consuming energy, towards what we have today and into the future with the bidirectional power flow. We have passive and active loads that consume, generate, and store energy. And we will have much more renewables, both in a distribution level and in a utility scale. And we will have more distribution and regional grids with the regional interconnections. And of course, we need to have an energy balancing and a power balancing. And this we will get with energy storage systems together with the long transmissions. And we will add demand response, renewable curtailment, and flexible power station. And due to these transportation sectors, we will also start to have moving loads. And to handle all this, to get it stable and to optimize it, we need to add intelligence. Now to the first example here. So I said earlier that the short circuit power is going down. Also, we could see that the inertia in the power system is going down. So on this slide, you can see the Europe, different countries, and a calculation of what the inertia is for each country. And you see some of the countries will be red in 2030, and that means that the inertia has gone down a lot, from a traditional value of 5 to 6 seconds down to 2 seconds. And what is the problem with this? So if you look to the left here, we see a very simple power system. And if we now lose a generator or we lose a line, that means that we will not have a power balance. And if we have too little power in the grid, then the frequency will drop. And if the frequency has dropped too much, we will disconnect generators and loads. Also, if the frequency drops too quickly, then the protection will disconnect our loads and generators, and we will get a blackout. And if you look at the figure in the middle here, it shows that if we have a lower inertia, then the frequency drop will go quicker, and we will reach a lower level of the frequency before it starts to go up again. And if we have a too high frequency change, or if it goes down too low, that is not good. And one way to reduce this frequency change, how to say, that then we could add inertia. And one way to do it is to use a synchronous condenser who has a rotating mass. But we believe that instead of a synchronous condenser, we should use an enhanced STATCOM. That is a STATCOM with a small energy storage and handles overload. And it has an advanced controller, of course, then to increase the performance. And what can we do then? So if we look in the figure in the middle here, we could see the frequency of the grid that we have simulated, and we assume we start with 50 Hertz, and then at 1 second, the frequency drops down to 49 Hertz. It reached 49 Hertz at 2 seconds, and then we keep the frequency constant. If you now look to the right figure, and then we start with a synchronous condenser and see the response of this frequency change. So that is the blue curve we should look for here. So the active power injection from the synchronous condenser is 0 when the frequency is constant, and then at 1 Hertz we go up with the power, and we get this injected power. And then at 2 seconds the frequency is constant again, and then we go down with the power to 0 here. Now we could emulate this with the converter with the storage, and that is the red curve. And you could see we could follow exactly what the synchronous condenser can do. But we could see here that we have oscillations, and that is not so good. And of course, with the controller, we could change the parameters in it, and then we could damp more, and then we could get to this yellow curve here that looks much better. But we can do even more than that. We could also increase the injected active power, and by that emulate a higher inertia, and this we cannot do at all with the synchronous condenser. And then we follow this curve here. And here we could also, at what we see at 2 seconds, then when the frequency becomes constant again, then we could automatically go over to a fast frequency response and keep up the injected active power to increase the frequency of the grid. And in this simulation case, we continue with this until the energy storage is empty, and then the injected active power goes down to 0 again. So by this slide, I just want to show to you that we have much more flexibility when using a STATCOM with an energy storage compared to a synchronous condenser. So we, within Hitachi Energy, we have now launched a product called HCC Lite Enhanced, where we take our STATCOM called HCC Lite, we add supercapacitors, and then we add an advanced control system into our controller that we call MAC. And together here we create HCC Lite Enhanced. And with this one, except for inject and consume reactive power, we can only also play around with the active power. And when comparing now, how good is this? So we could compare it with the traditional STATCOM and with the synchronous condenser. And here we have the HCC Lite Enhanced. Then we see that this HCC Lite Enhanced is better in all these cases here, except this one here, short circuit contribution. So here today, the synchronous condenser injects lots of current when we have a large voltage dip. And this overload current we cannot obtain with the converter today. Okay, now let's go to the example 2 here with the DC transmission. So I start briefly here with the history of HVDC. The breakthrough came in '94 in Sweden, where we put in a link between the island Gotland in the Baltic Sea with the mainland. And interesting here is that in this time we didn't have semiconductors, so we used the mercury arc valves. It was first in the 70s we started to use thyristors. And '97 we launched the self-commutated converters, or VEC HVDC with IGBTs. So why use high voltage DC? And here you could see a scheme how it works. We connect 2 different AC grids, and we want to use the high voltage DC to reduce the current. When we reduce the current, we also reduce the losses in the DC line. And DC, we want to use DC that then of course have no AC. And by that we can transmit power for a long distance with overhead lines and with cables. And we also decouple AC systems where we don't have the same frequency or they are not synchronized. And we started our VEC HVDC development '94, and we got our R&D demonstrator out '97. The power level was 3 megawatt. Here you could see how a photo of the site, how it looked like. And then '99, we had our first commercial project or a pilot on the island Gotland of 50 megawatt. And here you could see how one site looked like. And it was in this time here that I joined ABB HVDC. And now you could see where we are today. Today we could deliver up HVDC Lite, HVDC links up to 640 kilovolt and with a power rating of 3.5 gigawatts. And to the left here you could see a photo of how the converter looked like inside the house. So what we call on HVDC language, the converter is called valve and the house is called valve hall. And to the right here, you could see how a site looks like. And this site here is in Norway for the North Sea Link interconnector between Norway and UK. And on this slide, you could see the accumulated gigawatt installed globally for all manufacturers. And you could see here lately here how the power increases a lot. and it will just continue to go up here. This is quite fantastic. And then if we look at Hitachi Energy, or former ABB, so we have 200 gigawatts installed of our HVDC links today in the world, and that is around 70% of all HVDC installed. So far I've talked about VC HVDC, but we are also providing line commutated converters, thyristor converters for HVDC, and then we could come up to 12 gigawatt of power. Here you could see a number of applications what we could have with an HVDC or VC HVDC. So one part is of course interconnecting grids over a sea, where we could have different frequencies, or they are not synchronized, these grids. We could also connect to offshore wind when we have a long distance. We can have HVDC link in an AC grid. We can use HVDC to connect remote loads. This could be a mine, for instance. We could use HVDC to feed power out to installations in the sea. We can use HVDC for city center infeed. And we could use HVDC for connecting remote generation, like wind and solar. And we also provide HVDC application as back-to-back when we on land, how to say, want to connect two different grids that doesn't have the same frequency, or they are not synchronized. So far I've talked about point-to-point connection. Now we are starting to do the first regional DC grid in Europe. So today we have in operation in the north of Scotland, but you could see it to the right here, we have 2 stations. And now we are building a 3rd station on the Shetland that we will connect to this middle point that is called a DC switching station. And here the customer also have an option of installing 2 more links to provide offshore wind farm energy or power. And looking a bit more into the future here, so European Union needs 450 gigawatt of offshore wind by 2050. And how to handle that? So today we could call national distributed hubs. And we believe that into the future now we will start to have centralized hubs. And by these hubs, we can have connection to different energy markets. We can enable integration of renewables, and we can allow higher utilization of infrastructures. And the next step in this, that we call meshed offshore grid. And with this meshed offshore grid, we can allow a higher degree of renewable integration, and we can allow higher utilization of the infrastructure, and we can connect different energy markets, and we increase the redundancy, and we could optimize the investments. So this is the future scenario, what we see in the offshore wind expansion. And now to the last part of the presentation, where I will give you a snapshot of a future view of power electronics across the total power system. So here we could start to the left, where we have the generation area. So here, of course, we will have power electronics for wind and solar. We have pumped hydro. Of course, for renewables, we have collection grid. The collection grid could be AC or DC. We could have hydrogen with electrolyzers. We get electricity. We can have DC wind turbines connecting into an MVDC grid, and we can have microgrids. In this generation part, we can have STATCOMs and renewable storages. Coming to the grid, we of course will continue with the AC grids. So here we can have UPFCs, we can have AC power electronic protections, We can have utility storage and enhanced STATCOMs. And we have DC then, mesh DC grids with DC power electronic protections. And then we come into the industry and the large commercial sectors where we could have HVDC links, we have STATCOMs, we have static frequency converters, we can have STATCOMs with active filters, BESS. And when we come to the distribution, we can have a DC distribution with MVDC. Once more, we could use hydrogen to produce electricity and feed out in the distribution system. We go to the transportation sector, where we have the normal rail, we're going to have tram, and a bit more futuristic ships that we charge. And then we have a transportation sector with e-mobility and also electric highways. So this is just, as I said, a snapshot of different kind of power electronics that we could have in the power system into the future. And by that, I now come to the summary slide. So I showed you the energy transition is ongoing. We see an increased electricity consumption that will lead to an increased electricity production. We have a grid structure that changes. We go from a top-down toward an advanced interconnected grid with active loads and generation. I've given you 2 power electronics examples in the power system that supports the energy transition. We have this STATCOM with the energy storage that also provides inertia. And we have HVDC, where we interconnect power systems, generations, and loads. And we at Hitachi Energy, we are advancing the world's energy system to be more sustainable, flexible, and secure. And by this, I thank you for your attention, and hand back to André.
Thank you very much, Jan, for this very interesting presentation. I like particularly the last slide with the figure that you summarize what is the view that we will have for the future power systems with all of these different technologies integrated into this one figure. So thank you very much. This concludes our first part on the industry perspective, and I would move to introduce the second part, which is to be given by Pedro Rodriguez. So Pedro Rodriguez is the head of the Intelligent Clean Energy Systems unit at the Luxembourg Institute of Science and Technology. He's also connected to UPC, the Technical University of Catalonia in Spain, as a part-time professor. He has worked as Director of Technology in Modern Power Systems at Abengoa for several years, and also co-supervised large industry cooperation partnerships, such as with Vestas program in Denmark. Dr. Rodriguez is an IEEE fellow member, distinguished lecturer for his contributions in the control of distributed generation. His research interests include intelligent energy systems, distributed generation, and universal energy access. Before I pass the word to Pedro, I will just remind those who just joined that you can ask questions to both presenters, even during the presentations, in the questions box, and I will put them to the presenters at the end who will respond. Okay, thank you very much, Pedro. If you can start.
Okay, so thank you very much, André, for this very kind introduction. Well, today I will talk about this matter of grid forming converters, actually connecting to the presentation from Jan. Okay, these converters are the ones that could allow, let's say, work in a specific manner according to specific requirements. But in this presentation, in some of the approaches of this virtual synchronous generator, or this grid forming converter, is to emulate a synchronous machine. And this is actually the first point of my presentation. Okay, which is okay. Let's see exactly how to implement those converters, and it's really to know what is interesting when recreating the virtual machine or the synchronous machine. Well, the first I would like this just briefly to introduce our unit, the Intelligent Clean Energy Systems, which is a market-oriented unit open to develop solutions and services for modern energy system of the energy system of the future. We cover here mainly three main pillars. Okay, the first one, which is more related to let's say power systems and analysis, optimization, operation. There is another one which is more focused on, let's say, smart grids, automation, distributed control, power electronics, and in our third pillar, we are growing in this direction. Okay, we have a group of strong, let's say, background on artificial intelligence, but also we have an interesting lab or large lab on real-time hardware in the loop. And now we are developing several, let's say, living labs in Luxembourg. Okay, so well, let's move directly to this. Oh, sorry, this is let's say, just to characterize the product. Okay, the electricity product. Okay, which is just a pair of voltage and frequency, voltage, amplitude, and frequency. Okay, so the objective of the operator, which is in the grid, would be mainly cover demand, okay, secure supply, and ensure the proper voltage quality for users, okay, in terms of frequency and amplitude of the voltage. But on the other hand, should be able to do that within given stability limits, monitoring the grid state, okay, continually in order to react to any kind of, let's say, or to operate the system properly, and finally to be able to mitigate any contingency. Okay, so this slide is connecting to the one presented from Jan before. Okay, this could be understood as the let's say conventional power system, centralized power system, transmission, distribution, consumption. Okay, centralized operations, centralized markets, and in the future, as was mentioned, we will have, let's say, that system will be surrounded by other cells around at the distribution level, okay, where we will have local markets, local operation, and even as let's say Jan mentioned, these distribution systems could be connected in DC to other, so this transmission and distribution could be connected with multi-terminals to other centers. In addition, we are going to have some, let's say, DC-AC networks, which are in the internal interconnection. Okay, so well, from here, this system will pose several issues, okay, regarding complexity, uncertainty, but particularly it's something challenging from the perspective of the control engineering and power electronics will be the high dynamics and the abnormal reactions of the system. But this is why new definitions of stability have been proposed in the last years, okay, like the one here from power system engineering, where the conventional stability definition that was mainly focused on voltage stability, frequency stability, and transient or rotary stability, rotor angle stability, now is extended, okay, including the impact of the converter both in resonance stability and also in converter driven stability, okay, interactions with the grid, interaction with the shaft, interaction between converters, so it loads interactions, which are mainly giving rise to subsynchronous oscillations. Okay, so well, these interactions, okay, these new effects on the grid of these new phenomena had given rise to the publication of new requirements, new codes. More and more groups are studying today about this new conception of power converters, which should be responding to these new challenges. Okay, and in these new converters, you can see here, for example, one of the documents, one of the recent documents from INSOE. We are talking about new converters that would be able to create this intent voltage, contribute to fault level, sync harmonics, sync for imbalances, contribution of inertia. You can see something similar for NREL. Assume the responsibility of maintain the health of the grid, control the voltage magnitude, black start of the system to support, let's say, a standardized and adequate operational experience from the system perspective, or this one as well from the National Electric Corporation. You can see operation with low strength, okay, so low short circuit ratios, frequency stabilization, small signal stability, resynchronization, fall right through, system restoration, and black start. And well, I am a person who has been working for years with power electronics, okay, and I know we are talking here about grid forming converter, but if I was an engineer from 40 years ago or 50 years ago, I would understand, guys, you are talking about a synchronous generator, no? Operation with low strength, grid frequency, voltage stabilization, small signal stability. This is a synchronous generator able to support resynchronize. So is this what we are talking about? Are we talking about replicating synchronous generators? And this is actually, maybe let's take a look of synchronous generators. Okay, a synchronous generator is this, is a system where some mechanical power is transformed into electrical power. But this could be represented by this, let's say, second order equation. Okay, some inertia, some damping is in the middle, and there is an electrical interaction with the grid that could be simply represented by this simplified equation. Here, usually, this model used to be more complex. The fifth order model is quite common, but here we are talking about a third order model. But let's take a look at what happened with synchronous generators. It's so good, okay? Should we replicate now in the 21st century something from the 19th century? And we should take into account something, okay? The synchronous generator is only able to rotate in one direction, okay? Only with positive sequence, okay? Therefore, the synchronous generator is only rotating as a single speed, okay? It's really interacting with the fundamental frequency, but not with naturally with harmonics or surharmonics, okay? The damping of the synchronous generator from the very beginning of the regions is a problem of synchronous generator. The natural response of a synchronous generator is undamped, and it's necessary to integrate some dampers or some artificial mechanisms or additional mechanisms, no? The inertia has a given value, and this inertia we claim from inertia, but inertia is not always good. I mean, when you should stop the system, inertia is against you. Okay, when there is a fault, when there is it's necessary to really disconnect or speed up quickly a generator, the inertia would not allow to use that regular governor for doing that, and this is why actually it will be necessary to use PSS, which are actually directly regulating exciters of the synchronous generator. So the electromechanical response of the synchronous generator itself is quite slow. Let's say oops, what happened here? The impedance has a given value, okay? Of course, right, we are talking about just maybe transient impedance and synchronous impedance, okay? But at the end of the day, they have a given value. We don't have a given impedance for the seventh harmonic, another one for the fifth harmonic, another one for the negative sequence, okay? And actually, these impedances cannot be. These impedances, are highly inductive in a synchronous generator, pure inductive impedances, which are giving rise to interactions with capacitance and other elements in the grid, okay, during transients. And eventually all these parameters of the physical magnitudes are invariant, okay? It's not possible to change their value when operating. Therefore, is this really what we want to replicate? Clearly, using Pedro electronics will provide us new tools or new mechanisms for improving such a kind of response, okay? And let's take a look at synchronous generators, okay? And when we talk about the stability, you can see here the response from a synchronous generator in a let's say with a given inertia and damping, okay? You have here a kind of a stable response in the beginning. This would be an insufficient damping torque, okay? Okay, there is not enough damping torque and there is an oscillation because something was connected or some line or some tripping in a given time, and this is the regular undamped or unstable actually response, okay, from the frequency of the angle oscillation. And this is what we hear is we don't have, the synchronous generator doesn't have enough synchronization torque, and in a couple of swing cycles is directly disconnected. It's usually happen after a strong fault, for example, a short circuit close to the terminals. What happens if we increase in damping or inertia? Okay, what happens if we increase inertia? If we increase inertia of the generator, the response will be slower. Therefore, it will reach the let's say the instability limits later than before. Okay, the inertia is allowing that. Not in the case of transient stability, okay, but in the case of damping is fine. And what happens if we increase damping? Okay, if we increase damping, the oscillation, but not inertia, the oscillation will be, let's say, damped before, okay, and the frequency will remain, but again, the transient stability will be, okay. Therefore, this is the transient response of a synchronous generator. If we go, there is also the response of the voltage response of the synchronous generator. We know in general, power system, they have a given limit. Here we are representing this famous, let's say, figure regarding voltage stability as a function of the active and reactive power. But if we change the equation, we change the expression of the equation, we have this. And something that we can understand from these equations is the synchronous generator naturally will be able to provide reactive power as a function of the voltage at the point of connection. Okay, so in case of voltage drops because of any reason, the synchronous generator will have this natural and instantaneous response, which is actually required from the grid codes. Therefore, this is something that I consider would be interesting to replicate. If we go to see what is a power converter is a group of switches. Okay, so the power converter is able to generate a given, let's say, switch voltage that once interacting with the grid will generate a current with a little ripple, okay, because of the effect of the filters. Therefore, in principle, we could understand this, the voltage source converter as a voltage source, okay, sorry, here, it's a voltage source, which is determining the voltage at the point of connection, but this voltage source converter can be also controlled in order to determine the value for the current injected into the grid, okay? Well, what is the issue if we talk about a power converter, which is working as a pure voltage source, okay, regulating the voltage at the point of connection? The problem is paralleling, okay? There is, if we set here another voltage source, okay, there are no ways, if the impedance is very low, I mean, there are no ways, and even if the grid is powerful enough, there is no way for controlling the current, which is exchange between the sources, okay? Therefore, this is why it's necessary to, let's say, to propose, okay, or to integrate, or maybe physically, or maybe virtually, but to integrate some impedances in the case of the synchronous generators. I mean, we have here a kind of electromotive force, virtual electromotive force, a given impedance, which is giving rise to the interaction with the grid. In such a case, it's possible to regulate the current which is exchanged with the grid, and also in case of interacting with other sources, okay, is able, I mean, we are able to determine the power sharing or the instantaneous power sharing based actually on these short circuit impedances for these generators, okay? So, well, here we could try to emulate this by using power converters, okay? We could try to synthesize this voltage, just identifying, okay, we want to generate this voltage at the end of the day is equal to a given internal electromotive force minus the voltage drop in this impedance. What is the issue here? Calculating such a voltage drop entails this derivative term, which is a problem in terms of stability, okay? Therefore, sometimes when in some publications or some places it said, okay, a grid forming converter, because it is very similar to a synchronous generator, therefore it could be understood as a kind of grid forming converter. But this converter, if we consider a grid forming converter is the one which is controlling the voltage at the point of connection, we should be careful because of these derivative terms. But just using a Norton equivalent circuit, okay, this series connection of a voltage source with an impedance could be transformed in this order, and in such a case we can emulate, okay, we can regulate the current that could be circulating in this circuit, okay? Therefore, this would be the current that could be circulating in this connection, okay? This would be the current. So what we can do is, instituting a voltage source converter, we can use a current source converter, I mean the one regulating the current which is injected here, that would be exactly the same as it would be circulating in the point of connection, through the point of connection in case of considering such an electromotive force connected with an impedance, okay? So, well, from here, we can go directly to the two definitions of grid forming, or grid following and grid forming converters. This is maybe the most simple way of defining grid following. Is there is a converter which is injecting current in a given, let's say, connection point. For doing that, this converter doesn't have any idea about the state of the system, okay? This converter is just sensing the voltage at the point of connection with some delays, okay? Some delays, this is an issue. The PLL is integrating some delays, so it is giving rise to instabilities, mainly with this impedance is high, okay? And because actually the voltage at the point of connection will be a function of the current, which is dependent on this impedance, therefore the dynamics of this PLL is very relevant to determine, let's say, the stability of the system. And that's all, okay? This will be a system that will be just tracking or observing the voltage at the point of connection, and based on that, will inject a given current into the system for regulating, I don't know, the power, the voltage at the point of connection, whatever, okay? A grid forming converter is something different. A grid forming converter, what is regulating is the voltage, the internal voltage, okay? And this internal voltage will have some memory, okay? This converter, this voltage is memorizing by the effect of some integrator. This integrator could be inertia, could be any algorithm, which is the coupling, the dynamics of this voltage to the instantaneous dynamics. I mean, respect to the instantaneous dynamics of the grid, okay? In such a case, the state of the converter, internal state of the converter will remain unchanged in case of any disturbance, and automatically the converter will react to such a disturbance, as in the case of a synchronous generator, and progressively will move to a new coherent operation state after the disturbance is let's say, or the perturbation is removed, okay? So, well, this is, so the behavior, I mean, this is a simple, this is a simple, let's say, representation of what we consider a grid forming converter is. I mean, it's like biking, okay? When in the term of biking is not a matter of observing where the pedals are and stepping on, okay? It's not a matter of observing where the pedals are and stepping on. It's a matter of just pedaling, okay? It's a matter of moving synchronous to the system, okay? So this is the matter of grid forming converter. Grid forming converter will generate an internal electromotive force, an internal sinusoidal voltage that will interact with the grid voltage and will be naturally synchronized. Of course, a grid forming converter could be better represented in the case of a tandem, because the grid forming converter will not work alone. It should be able, a grid forming converter, it should be able to energize the system. I mean, a cycler or a biker should be able to ride along this tandem bike, okay? But in addition, should be able also to cooperate with others in order to ride the bike according to the capacity. So according to the, let's say, the parameters and the intention of such a power converter. Therefore, this is the matter, okay? A grid forming converter should be able to energize and to form the grid, but also should be able to cooperate to other with a given strength to maintain the stability of the grid. So this is a grid following converter, according to what we explained, and this is a grid forming converter, right? We are talking about switches. Both of them are exactly the same, okay? What is different are the algorithms, of course. I mean, understanding they have the same thermal limits, the same voltage limits, the same switching. Therefore, in such a case, both converters will be equivalent to each other, okay? The difference is in the algorithm that is implemented there. Therefore, I'm talking about this virtual rotor, the virtual impedance. It's a matter of finding some mechanisms for understanding or for providing some physical, let's say, meaning to the algorithms that we are coding here. But there are many ways of implementing a grid forming converter, okay? I mean, there are main pillars, okay? One of them would be defining how do we synchronize, okay? We can synchronize based on power balance, but we could also synchronize based on voltage, okay? We can have several PLLs, some fast PLLs for react to fault, some slow PLLs for reacting to electromechanical dynamics. That is perfectly feasible. Therefore, in the same manner, it would be possible to determine what is the electromechanic interaction, the electromechanic behavior of the grid forming. It could be based on mimicking the synchronous machine. Some approaches are in the direction, or it could be based on generating any other kind of oscillator based on a digital implementation or any kind of other mimic that is generating such a kind of virtual rotor internally. The same for the electromagnetic interaction. We can think on impedances, or we can think on admittances, okay? In one case, we should deal with derivative terms, or maybe with some algebraic transformation for dealing with such a derivative terms, or with admittances that are related to integrators are maybe easier. And of course, the external loops, they are essential, okay? The loop, I mean, the virtual governor or the virtual AVR, the loop for frequency and voltage respectively, and and also even the synchronous internal controllers. Okay, so there are many mechanisms. Therefore, for indeed, let me just present in you two maybe applications a little bit more advanced. Okay, as you mentioned, sometimes we talk about grid forming converters as a kind of different hardware, different features, but depending what we want to do, okay, we can do it externally. Okay, therefore, if we consider, for example, this is a typical grid following converter. Okay, if we want to take to have a kind of inertial response, this inertial response in this case is taking around, I don't know, 20 seconds, okay, and it is very fast. We are talking about a low inertia here, okay, with the inertial response could be even longer. So why to calculate this inside of the power converter? Okay, we can have just a communication link where the power converter is providing the instantaneous power delivered, the instantaneous frequency, which is read by the PLL, the instantaneous voltage. Okay, we don't mention angles here, so we are not attacking or we are not against any transient stability. Based on that, we can calculate the swing equation and determine what should be the power reference for emulating such an inertia externally in a conventional grid following converter, the one you can buy for a PV panel, okay, which is really cheap, PV panel or PV plant, okay. So, and this algorithm is nothing. What the matter of this communication? These communications here we are considering 20 milliseconds, and here we are, I don't know why it's not written, and here we are considering 100 milliseconds. In 20 milliseconds, you can establish a peer-to-peer connection with any kind of, let's say, protocol, Modbus, whatever you want, okay, for CAN bus, okay. So, well, this is actually the result from one of the projects we are developing. Flexitron storage, a project which is developed here in LIST, and it is the results are from the PhD dissertation of one of our students, Engo Baulai. And also here you have a more extended implementation of this external controller. Okay, in this case, you see here we have the variation in power, a given, let's say, swing equation, a given electromechanical equation, and at the end of the day, it's giving rise to a given variation of omega, variation of delta, and from here we determine what is the load angle, okay, or the position of the electromotive force, okay, the angle. The same regulating the reactive power, we can determine the amplitude of the excitation, okay. Using the formulas we mentioned before, we can transform, for given impedance, we can transform angle and amplitude of the excitation into given P and Q, okay. Therefore, this is the P and Q to be developed by the converter, and in this case, we are applying this to a plant, okay, not to a single grid forming converter. Here we are talking about a grid forming power plant. In this case, we are managing several power converters, and this capability of emulating inertia is implemented here at the point of connection according to this algorithm. You can see here the effect. These are real results. In the previous case were also real results, and here you can consider the effect of the damping, how the oscillations are decreased, okay. And here you can see what is the importance of, I mean, this is the response of the system when we were playing with 4 independent grid forming converters. You can see these oscillations here, only with 4, okay. In the case of having a centralized grid forming virtual synchronous power plant controller, in this case, sorry, you can see how the oscillations are dramatically decreased. Therefore, in the future, when many power converters, grid forming converters will be working together, we will have this kind of high frequency modes between, this is something already happening when in a power plant at high frequency, and in such a case, such a kind of coordinated synchronization will be needed, okay? Well, so from here, I would like just to show you this, okay? Consider this is the frequency response. I am stop now, Andre. Therefore, this is the frequency response as Jan mentioned so before. In the case of a given contingency, a given power imbalance in the grid, this would be the evolution of the frequency for a given inertia and damping. What would be the result in case of increasing damping? This damping is in this case increased because we are increasing the coefficient of the droop control, and you can see how the steady state error is decreased, okay? So what would be the response of the system in case of decrease in inertia? This would be the one you have here, the half of the inertia before, and this would be the result of decreasing inertia and increasing damping. So you can see this last response is much interesting than the first one, okay, and much interesting than the other. Therefore, inertia is something that we should use today because our system today requires to have some kind of compatibility. But if we think on system in the future where it's consisting only on power converters and in which the capacity of control and sampling is fast enough in order to be able to increase damping in an effective manner, in the future, maybe inertia will not be one of the requirements. Let's say a HVDC system, which HVDC system disconnected from the grid. In such a case, inertia maybe will not be a requirement. With this, thank you very much. I stop here. Sorry for extending myself too much, and thank you for your attention. Sorry.
Thank you very much, Pedro. And now it's time. We don't have much time, but let's extend a little bit
open to any
answer
question.
some questions. So the audience has already put some questions in their boxes, and I will go through some of them. So maybe the first one I think is more directed to Jan. Does it exist any MVDC applications? What can you tell us about this?
Yes, I think there are MVDC applications, but customers, they always prefer the cheapest solution, how to say. So I think today MVDC is a bit too expensive.
Okay, thank you very much, Jan. Another question. Are you worried by how a 100% inverter-based generation would break short-circuit currents? I think this can be to either one of you.
Yes, I would say it like this. From the beginning, we had no inverters at all. And now with a lot of renewables in some grids, we have come up to 50, 60% perhaps renewables, and they have converters connecting to the grid. And then we need to add new grid codes, new rules on how the converters should act towards the grid. And here the grid forming controller that Pedro has displayed here is very important. And when we take the next steps, we go up even more with power electronic connected renewables, then probably we need to strengthen the requirement even more. But this is, of course, possible.
Thank you, Jan. Another question is there any application for virtual synchronous generators, voltage source converter that emulates synchronous generator behavior to increase inertia of a system as of right now?
There are several applications. Oh, sorry. Go ahead, Jan. Sorry.
No. I mean, we have a product out now, and Siemens, they also have a product out. So yes, and there is a market.
Yeah, and actually, well, for example, I don't know, it was in the last week or some weeks ago, the large in Australia, no, that the large BESS system, 100 megawatts, is operating already as a grid forming converter. Okay, with modulating inertia from the grid. In our case, in our projects, we're installing several megawatts of power converters, and these are funded in islands, okay, and in remote areas with inertia. And years ago, in 2000, I don't know, 11 or around, we developed it in Chile. There is a plant, 100 megawatts PV power plant, which is already implemented, and this plant has also 12 megawatts of battery energy system on all them use grid forming algorithms. Yeah.
Mm-hmm.
Thank you. Another question is, recently there's a new idea of PV StatComs. Do you think that these small PV inverters cumulatively can solve the whole grid problem, or the control interaction among them can create even more problems?
I would say like this, active power is floating very simple through the power system. Reactive power is difficult to transport. So you need to produce a reactive power where you need to use it. So therefore the whole grid needs reactive power, and therefore you need to distribute out the reactive power compensation, we could say. So you cannot only use solar PV inverters to provide reactive power for the whole grid.
Yeah. Yeah.
Perfect, thank you. So another one, maybe this is one that's more generic. So taking into account that real energy transition has just started, so we still rely a lot on fossil fuel up to now. How realistic are these ambitious renewable transition scenarios that will expect it to become a reality in 30 years? And considering the amount of infrastructure that has to be changed, not only regarding production, but also distribution and consumption. Do you have any comment?
Yes, I think this is a political decision. We start to see a climate change, temperature increase. So I think it's a society problem where in the end the politicians need to decide what to do.
I would like something, or I would add something as well, Jan, in this direction is years ago, only 5-10 years ago, we were very concerned about efficiency, okay? We all us were interested in designing converters 99.7 efficiency for PV, okay? Today, people is more aware because of different reasons about security, about resiliency, okay? Grid forming converters, these kind of technologies are a solution in such a direction. Therefore, this is why today there is a market around macrogrids for harbors, for strategic, let's say, grid, airports, fortresses, okay? So there is a market, okay? It's still restricted to some specific application where security particularly is very important, security of supply and stability, but of course it will be expanding, okay? And what is clear is all companies today are focusing on addressing, all manufacturers are focusing on addressing this topic, and the grid codes are already reacting in such a direction.
Thank you very much. One more question. So this is more, let's say, I think for Pedro, on the context of Luxembourg. So how does this kind of solutions contribute to improve or solve the issues in the electrical grid for the specific case of Luxembourg, considering the amount of electrification of energy usage that will be foreseen for the next years?
Well, Luxembourg is a very critical, it's a particular case, okay? It's a country which is importing 85% of the electricity, absolutely dependent on Germany. Tomorrow, Germany will already is installing a lot of HVDC corridors. It's probably in a few years. Actually, it's already expected within the priority projects from ENSOE in the future, in a few years. I mean, the next connection will be to Germany. The second one will be to Belgium by using HVDC. As soon as we do that, okay, it's logic to understand, okay, it would be interesting to provide grid forming capacities to such a converters, because in case of any failure, the grid could be able to be maintained. And on the other hand, particularly as we're talking about Luxembourg, Luxembourg is aiming to multiply by 6 the PV power capacity in the next from now to 2030, and by approximately 3 for the wind power. So all these capacities should be able to survive to any fault, and also to let's say to be able to maintain the grid and to provide this kind of let's say advanced services. Okay, therefore, yeah, in the case of Luxembourg, there are reasons why, even though of course Luxembourg is in the middle of 3 countries, therefore it's very well interconnected. So, but in case in the future local generation and local demand, energy communities, districts, and so on are more relevant, interconnection will not be able to solve the local problems, okay, the ones in the last mile of the feeder, okay. The same as we mentioned before for reactive power, it could be applied to Black Star from the last mile of the median or islanded operation of energy communities and districts. Therefore, grid forming is a solution. Yes.
Thank you, Pedro. Just because we are already 5 minutes past the time, I will do just one final question before saying goodbye. One question is on how would the power balance be maintained on a system where inertia is no longer a priority, as you said in the presentation, Pedro?
Well, we can consider, Jan, please, but you can correct me, but if we consider, for example, a DC macrogrid, of course, it's good to have some capacity, okay? Some energy stored in the DC bus, okay? But if you consider today a DC HVDC connection, the energy which is stored in the DC bus is very little, okay? It's just for covering 2 milliseconds, something like that, okay? Therefore, no energy stored, okay? One half of CV squared, which is absolutely equivalent of one half of J omega squared, that would be the electromechanical translation, is nothing. Therefore, inertia, equivalent inertia in such a system, which is operating today, is nothing. Therefore, a system which is fully based on power electronics would be able to survive if it is able to respond fast enough. And of course, controllers are taking into account all the new reactions. Therefore, modeling and analysis and design of everything there should be much more careful as we do when we play with synchronous generators. Yeah. I don't know, Jan, what's your point in this direction?
Oh, yeah, you had a good answer.
Thank you very much to both of you. I think now we're already 6 minutes past time. So I would thank you for your presentation, and thank you also to the audience for their questions and their interest. And before we say goodbye, just to say that the presentations will be made available for downloading in the website 1 or 2 days after this webinar. So we are free to share this with you. And hopefully we will see each other soon. As I told you, this is the first of a series of seminars. The next one will be in March, so stay open to see what will be about. And this will lead eventually to the final Energy Transition Dialogue Day that will happen here in Luxembourg on the 30th of June 2022. More news to come on this. So thank you very much all for attending, and thank you especially to our presenters and for their help and their brilliant job in this webinar. Thanks a lot.
Thank
Thanks.
you.
And bye.
Thank you. Bye-bye.